Okay, but before I would like to play a game with you. So, do you know what it is? It's a prismatic joint. It's also called a dove tail. You know, it looks like a dove tail, a bird. You know. So it has 1 degree of freedom, 5 constraints. It allows the motion along one axis, right? The question for you: does this thing is able to move? No. Is anybody that thinks that it's able to move? It can't. So all of you thinks that it doesn't able to move, right? Right. It's not prismatic joint, but still. I didn't say that it is prismatic joint. The first one was prismatic joint. That one was prismatic joint. My question was, does this thing is able to move? So that one is prismatic joint. Everything is obvious. And the one that I just showed you is it clear now? Okay. I didn't finish. Is it the only way to do the motion here? It's like, yeah, it depends on the shape. Do we able to do the different kind of motion? Opposite direction, it's just boring. My point here is that beside that we can actually do a very different kind of solutions. You didn't see, and this is the point, that sometimes you can see the situation and you think that you do understand it, and you already know everything about it, and you think that you can predict how it's going to behave, but actually your prediction is wrong, because it's based on your previous knowledge and your previous background. And when we trying to do something new, we need to think out of box, and always think about the new solutions. One final point, one final simulation. Since we talk about the simulation, sometimes even this kind of prismatic joint will behave like this, because we can see the simulation. Sometimes it's just nonsense. All right. Our second lecture is called Modeling for Simulation, Bone Graphs, and How Do Simulators Work. So we do remember all this stuff. Now we do remember this. Okay, so the goal for current lecture is to understand what is inside. So let us suppose that it is a simulation package, and we're trying to understand what is inside and how does it work. Okay, we just derived Euler Lagrange equation for mass spring and damper system. And what we have done, first of all, we did the analytical math modeling, and only then we have created the graphical block diagram. a graphical representation. It's for the block diagram, which is one that has one direction. You know, when we have created the system, everything it flows in one direction, right? When we have integrations, it do not flow in opposite direction. If we want to have a loop, we need to have a feedback system. But bond graph, it's something different. We have rules in order to create the graphical representation first. Only then it can be used to derive analytical model if we want. But actually, already the graphical representation can be used for simulation. It's for you to have an intuition what is the difference between block diagram and bond graphs. So what are the bond graphs? Bond graphs were invented in the 50s at MIT, and it was one of the first methods that allows us to automatically derive the equations. The idea was to create the computer program that will do the simulation automatically. By Professor Pitor, that you can see in the picture. Okay, before we consider the main intuition of the system, we need to play a little game here. But first of all, we need to remember the vector space. The vector space has origin, it has a scale product, it has vector sum. So vector space is all about multiplication of a vector. So vector is like an arrow, list of numbers, it's a vector, right? We can multiply it with the scale, and we can sum vectors between them. It's like we have an arrow, another arrow, we can sum to have another arrow, and that's it. We cannot multiply vectors between each other. Multiplication is a property of Euclidean space, not a vector space. So when we want to multiply force and velocity, it's something actually, force and velocity, those are not elements of vector spaces. Because in vector space we do not have an inner product. We cannot do the multiplication. We can do a multiplication only in Euclidean space. So when we talk about the multiplication of force and velocity, what we will have? Force and velocity? Power, right? We'll have power. And velocity is a vector. It belongs to a vector space, but the force is something else. It's not a vector. It do not belongs to a vector space, but it belongs to something which is called dual space of linear operators that you can think about like a linear operator on a vector that gives you power. So let us suppose that we have system A and system B. And we represent in system A and system B the same force and the same velocity. Since it's different coordinate systems, it has different numbers, but the product of force and velocity have to give us the same result, because the power is independent of coordinate system. All right? So it will be the same. Forces will be different, velocities will be different, but the product will be the same, because the power must be the same. Power is physics, it do not depend on the choice of coordinates. All right, if we have two different coordinate systems, it means that we can go from one system to another system. And there is some matrix A. Actually, we need to use a homogeneous transformation matrix, but I'm not explaining you what it is, just some matrix A, matrix that describe the relation between frame A and frame B. All right, we can put it inside. We can get rid of velocity B because it's in the left and the right part. We'll be left with this, and out of that we can derive FA, right? When we do transpose AB, transpose will be B transpose A transpose, right? Is it clear here? And if we want to express FA, we will have the following. Are you sure? Do you agree? And here you can see that the matrix of relation is different. So they transform differently, velocities and forces, because they have different nature. Velocities are vectors and forces are covectors. And multiplication of vectors and covectors always give you power. Okay, yeah, I already tell you that. So the idea is the following. Idea of bond graphs, that we have two systems, system A and system B, and they interact between them due to the power exchange. It's like when we hit acceleration in a car, the car moves not because of the fact that we hit the acceleration, but the fact that there is a fuel, we use fuel energy to move a piston, a slider in the internal combustion engine. The slider moves crank in the crank slider mechanism. Crank moves shaft, and shaft is attached to the wheels. Wheels interact with the ground, and each piece of this system interacts with the energy. So we can describe interaction of those two systems A and B by a power flow. This half arrow describes the direction of power. So here, power is go from A to B. And in order to get power, we need two variables, something which is called an effort, E, and something which is called flow, F. Effort, it's something like force, and flow, it's something like velocity. So flow is a vector, effort is a covector, and if we multiply them, you will get power. So two variables. It's not only one now. We have two of them, and they orientated in the different direction. Can you see this stroke, red stroke? It's called causality stroke. It means what causes what. In this case, it denotes us that flow goes from A to B, and the effort goes from B to A. You can think like it is an arrow. An arrow, its direction of flow, or you can think of like a pump that gives force. So flow in this direction, force in that direction, flow in that direction.
The effort is the covector as flow is vector?
Correct. And effort and flow are called power variables. And if you integrate them, you will have energy variables. For example, velocity. If you will integrate velocity, you will get x, position. Position is proportional to the energy. Kx in power 2 over 2, so k coefficient of stiffness is constant, so energy is proportional to the deflection, right? force. If you integrate force, you will have a momentum. So, do you remember the second Newton's law? F equals to ma. But it's wrong.
It's MP dot.
At the p, it's p dot.
That's order.
Yeah, because if we derive it, we will have mv dot plus m dot v. In most of the cases, mass is constant and it just goes to 0. But if you want to create a robot with internal combustion engine, fuel goes down, so mass will be different. And for the car, the mass is not constant. So p dot. And if we integrate force, we're left with the momentum. And actually, we can find those efforts and flows in every domain. In mechanics, force and velocity, or torque and angular velocity. In spatial mechanics, it will be wrench and twist. We'll take a look at this at the end of our course. In electronics, it's voltage and current, or in hydraulic, pressure and volume flow rates. But actually, it's true for any kind of physical domain. For chemics, also. So, chemistry, fluids, continuous spaces like air and water. It's also true. It's very fundamental. So we can think of energy as a language to describe interaction of elements. And initially it was used in order to create a first simulation package, but now its tool can be used to better understand how the system behaves. This tool is not very popular. Maybe you saw it, but still it's pretty rare. It's very popular at MIT and the University of Twente because they collaborate a lot. And for example, we will take a look at the impedance way to control a robot. And if you read an initial article by Neville Hogan, you will see that he uses bone graph notation. Also, if you will be reading articles of Stefano Stramijoli, which is Vice President of EU Robotics, he also uses it a lot. And this methodology allows him to come up with new insights how to create more performance and more intelligent robotic systems. More than that, power and energy is coordinate free, and it allows us to come up with a way of notation and description of motion of rigid bodies, and not just rigid bodies, which is coordinate independent. And I will be explaining you twists and wrenches that will be the same, that do not depend on your coordinate system choice. Sometimes it's if your results depends a lot on the coordinate system, it leads to errors. But this way of notation, way of modeling, can help you to get rid of these mistakes. All right, so what are the advantages? Besides the fact that it allows you to better understand the physics of your system, it also allows us to describe different kind of fields, physical domains in one system. It's like you can create a simulation model that consists of electrical parts, mechanical parts, hydraulic, thermal, chemical, biological system in combination of it. I'll show you a few examples of it. Methodology is useful in multidisciplinary field of nature and mechatronics. It's the one. Initially, the aim was to generate math models, and still it also allows us to better understand how the system behaves and gives us new insights. All right.